did the mic check. Thank you. We're going to discuss independent events. Remind you of what it means for two events to be independent. And you don't have to copy this. I mean, it'll be on the video. So maybe just kind of try and soak it in. Two events are independent if the outcome of one does not affect the probability of the other. So if I tell you, what happened with one event, the chances of success or failure on the next event are still the same. So it doesn't affect it. So let's look at the event of flipping two different coins. Now, in blue here, I've got what's called your sample space. These are all the different things that can happen when you flip two coins. You can get two heads, a head and a tail and a head, or two tails. So there's four different things in your sample space here. And what I want to look at is the probability of getting a head on the first flip and the probability of getting a head on the second flip, or these events. So the question is, are these events independent? Does getting a head on the first flip influence the head on the second flip? So what I'm going to do is I'm going to calculate these two probabilities. Probability of a head on the second flip, and the probability of a head on the second flip, given that you got a head on the first flip. So the second one is your conditional probability. And it's a notation that you might not be very comfortable with yet. So let's go through that a little bit more. Probability of heads on the second flip, given that the first flip was a head. That's what this is saying. So the first event has already happened. You got a head on that first flip. That's what it's telling you. Now let's calculate the probability of a head on the second flip. And we're actually going to calculate both of these. Because if H1 and H2 are independent, then these probabilities should be the same. Probability of getting a head on the second flip shouldn't be influenced by what happened on the first flip. So let's calculate these probabilities. Looking at the probability of H2, there's four things in my sample space. So all these four different events. Out of those four events, how many of them have a head on the second flip? Two. So the probability of a head on the second flip is 2 out of 4, or 1/2. Now, let's look at and understand the second one. For the second one of these, I'm telling you, okay, I've already tossed the first coin and it landed heads. So that restricts my sample space. It's no longer everything that's in blue. It's now what's in pink. So, okay, now my sample space consists of two events, both of which have a head on the first flip. What's the probability then that I get a head on the second flip, given the head on the first flip? Yeah, there's two outcomes, and only one of them has a head on the second flip. So I get 1/2 either way. And it kind of points to a result that I think you could have figured out for yourself, that flipping a coin leads to independent events. The coin doesn't have a little chip inside it saying, you know what, I've come up tails 5 times in a row. It's time I come up heads. Although, interestingly enough, I think for pro football, I think it's the NFC has won the coin toss in the Pro Bowl like 15 years in a row. It's really uncanny. I mean, that's a huge improbability, but whatever. Probability of a head from one flip to the next is going to be 50%. In other words, these are independent events. And that's what I want to emphasize, that they're independent. What that allows me to do, if I have independent events, is to work with probabilities in a little easier method. Probability of H1 and H2, if they're independent, can be calculated as the probability of H1 times the probability of H2. So if I want the probability of a head on the first flip and a head on the second flip, I can calculate that by the product of these probabilities. What's the probability of a head on the first flip? 1/2. probability of head on the second flip? 1/2. So a total of 1/4. Another way I could work that, and it's easy in this particular case, is that I know there's 4 things that can happen. Only one of them out of those 4 represents the probability or the event of having 2 heads. So 1 out of 4 chance either way. But I can do this because these events are independent. And that's the key thing here. That's what I'm trying to emphasize, is that you can turn this into the product of 2 probabilities as long as the events are independent. The outcome of one does not affect the probability of the other one. Just like, if you're having kids that, the first one's a boy, probably the second one was a boy, hasn't changed, all right? There's no mechanism by which one of those can influence the other. Okay, so that's kind of a little bit of a review, but it's also a little bit of a lead into our first problem. I'm actually going to do one of your homework problems for you. It's problem number 1. So this is section 5.2. So problem number 1 talks about some drone deliveries. Who amongst you are ready to have a little flying machine drop off a package on your porch? You comfortable with that? So I got 1 and a couple. All right. So according to this survey by Brittany Bowes, 42% of consumers are comfortable having drones deliver their purchases. Suppose we want to find the probability that when 5 consumers are randomly selected, exactly 2 of them are comfortable with drones. What is wrong with using the multiplication rule to find the probability of getting 2 consumers that are comfortable with drones, followed by 3 consumers that are not comfortable, as in this calculation? So you got a 42% chance of somebody being happy with them. You got 2 of those, etc. 3 that aren't. Let me give you some notation and we'll kind of look at things here. So this is problem number 1. So I'll call that the probability that the first consumer is happy and the second consumer is happy. You been drinking again? Oh, kidding. All right, no, thank you. And the third one is not happy. And the fourth one is not happy. And the fifth one is not happy. Well, these 3 aren't, those 2 are. So here's a kind of a compound event where 2 people are happy and 3 aren't. Is it reasonable to assume that these are independent events? That is, your opinion on this subject has no relationship to somebody else taking it random. Is that a reasonable assumption? Yeah, seems pretty reasonable. And because it's reasonable, I can turn this into the product of probabilities. And that was the point of kind of our discussion before this problem. And these probabilities were, what, 0.42, 0.5, or 0.42 again, 0.58, 0.58, and 0.58. So there's nothing wrong with that calculation as far as this is concerned. But I'm not sure that this is exactly the probability that they were asking for. If you take a careful look at the book, they ask you to find the probability that when 5 consumers are randomly selected, exactly 2 of them are comfortable with drones. So what's wrong with this? I mean, you can do this one out on your calculators. In fact, let's do that. The way I would do it is type in 0.42 and then hit the square button. times 0.58 raised to the third power. So that raise button is right above the division sign, raised to the third power. And I think I'm going to get something, whoops. Oh, I forgot to put the decimal in the first one. 0.42. There we go. So overall, about a 3% chance maybe that would happen. But there's really more to this probability than what we have here. Because what they assumed is that it was the first two people that were happy and the rest were not. But the problem asks for the probability that two people are happy. Does it have to be the first two? No. It could be, say, the first and the third person. It could be the first and the fourth person. What else could it be? First and fifth. And then let's keep going from there. It could be the second and third, or the second and fourth, or the second and fifth, and so on. Third and fourth, third and fifth, or fourth and fifth. So, wow. Realistically, I would have to add up all these different possibilities. So that's kind of a pain. I wouldn't want to have to multiply them, then I'll add them up. In fact, there's kind of a shortcut here. And that is, instead of adding this up repeatedly, what else could I do? We could multiply it. Multiply it by however many there are here. Now, rather than counting, let me kind of zoom in a little bit before you actually do all the counting. Rather than counting by hand, let's see if we can't find a more sophisticated way to count. I want, of those 5 people, I want to choose exactly 2 of them that were happy. So is that a permutation or a combination? So, good question. Does the order matter? Does it matter if it's the first and the third or the second and the fifth? The order doesn't matter, right? It's just 2 of them. So if order doesn't matter, that's combination. Thank you. Appreciate it, John. All right. So take out your calculators or Google and calculate 2, choose 5. And see if you can't predict how many lines I have on this sheet. Or 5 choose 2? My bad. 5 choose 2? Yeah, 5 choose 2. Thank you. Oops, don't want that one. So on your graphing calculators, type in the 5. The math key over to probability. Third option down, 5, choose 2. You should get 10. So everyone able to get 10 out of that? You can do it off of Google Sheets too. It's equals combin and then n choose r. But you get 10. And that matches what we have here. There's 10 of these different probabilities. So if I wanted to figure out the probability of getting exactly 2 of them that are happy and 3 that are unhappy, it would really be 10 times that probability. So let me go back up here, grab that probability. Oh, no, wait, it's not in here. All right, so let's calculate it again. Oh, no, here it is. This times 10. So about a 34% chance of getting exactly 2 people that are happy out of the 5. That's the correct probability that we need here. Now, this kind of experiment leads to something called a binomial random variable. And that's really the whole point of this section, is to find probabilities that match this. And to try and clean up our calculation of this. Because you're not going to be asked to do something anywhere near this. We're going to fill in some formulas. In fact, we're going to have some technology fill in our formulas for us, which is even better. So we don't have to worry about plugging lots of little things into our calculators. So let's work on understanding a binomial random variable. What leads to a binomial random variable? So, binomial random variables. There's 4 requirements for a binomial random variable. Binomial random variable is the result of an experiment that has a fixed number of trials and that's n. It has independent trials. So we discussed independence earlier. The outcome of one does not affect the probability of the outcome of the other. There are 2 possible outcomes. Generically, success and failure. But it could be heads and tails. It could be boy or girl, Democrat or Republican, maize and blue or Spartans. But 2 possible outcomes. And finally, the same probability of success throughout the experiment. Okay, so you can leave a little room underneath here. In a little while, we'll write the function that calculates that. But right now, let's see if we can't figure out a couple of binomial random variables, or whether or not certain experiments lead to a binomial random variable. So we'll start with problem number 6. Clinical trial, the Y-sort method of gender selection developed by the Genetics and IVF Institute was designed to increase the likelihood that a baby will be a boy. When 291 couples use the Y-sort method and give birth to 291 babies, the genders of the babies are recorded. So the question is this going to be a binomial random variable? Is it the results of this trial, are they going to represent a binomial random variable? So let's look through our list. And I'm not sure if you noticed it, but I did write this out in a particular order to try and help give you a mnemonic. Did anyone catch that? Does anyone see a clever way that you can decide whether or not these things add up to a binomial random variable? It fits. So when you're deciding if something is a binomial random variable, see if it fits. So for problem number 6, do we have a fixed number of trials? Yeah. Yes. N equals 291. So that's the first one. Are they independent? Are the genders of these babies going to be independent? Yeah, what happens with one doesn't affect the probability of the other. So yes, independent, sure. Two possible outcomes, yes, boy and girl. Is it the same probability of success throughout the experiment? Is the probability of boy or girl going to change from one couple to the next? No. Now, it doesn't have to be a 50-50 chance. It could be anything. If I remember one of the earlier problems like this, there was like an 80 or 90% chance of success. If you're defining success as being a boy, or you could also do it as being a girl, but that probability is going to be consistent throughout the trial. So, again, yes. So this is a binomial random variable. Yay, that's what we want to see happen. Let's move down to problem number 8, unless there's something about problem number 6 that's still bothering you a little bit. Okay. Let me put problem number 8 up here then. Yeah, Charbel? So the probability of success has to be the same throughout the trials. So let's keep it easy and assume that this method has no influence on the probability of conceiving a boy. And the probability of having a boy for the first couple is 50-50. And for the second couple, it's 50-50. And for the third couple, it's also 50-50. So that probability remains the same throughout the trial. It's like flipping a coin. Each time you flip it, you have a 50-50 chance of getting a heads. And that probability is going to remain the same throughout your trial. Okay. Anything else on 6? Let's move on to 8. In a U.S. cellular survey of 500 smartphone users, subjects are asked if they find the abbreviations such as LOL or BFF annoying, and each response was recorded as yes, no, or not sure. So let's work on this one and try and decide for ourselves if we think it's a binomial random variable. So the first thing, are there a fixed number of trials? Yes. There was 500 smartphone users, so yeah, n equals 500. Are the trials independent? Yeah. If you're asking cell phone users at random, what do you think? What do you think? Those opinions are going to be independent of one another. And I will have a little bit more to say about this later. What's the third one? What's our third option? 2 possible outcomes. Are we good there? No, because it was yes, no, and not sure. All right, third one was, not sure. So it fails it. No, there are 3 outcomes. So we can stop here. Doesn't matter what happens here. This is not a binomial random variable. And that's it. It failed that third one. Now, when we're sampling here, we took 500 people. What would you assume is the population? Because it is a sample. What do you assume that population is? Who are they sampling from? Where are they sampling? What would you define as the population? Yeah. Smartphone users, all right. Yeah, smartphone users. We don't know exactly the ages, but they're smartphone users, so they got to be somewhat old. Hopefully you don't give a smartphone to a 2-year-old, but the bottom line is that there's a lot of smartphone users out there. There's tons of them. And presumably you're not doing this sample with replacement. You're doing it without replacement. Technically speaking, when you sample without replacement, that leads to dependent events. But let me remind you of something, and it's called the 5% rule. We're going to see it a little bit in the next two examples. So the 5% rule says that as long as your sample size is not more than 5% of your population, then you can treat your samples as being independent events. Let me illustrate with numbers from my morning class. In my morning class, there was 7 girls and 9 males. All right, so a total of 16 people. If I wanted to look at certain probabilities, probability that I get a girl on the second pick, and a probability that I get a girl on the second pick, given I had a girl on the first pick, let's take a look at those probabilities. Now let's see. Now let's just call it the probability of getting a girl on the first pick. If I select a girl at random from this population, what's the probability that my first pick is a girl? 7 out of 16. Now that I picked a girl out of that population, and assume that I'm not returning that girl to the population, what's the probability of getting a girl on my second pick, given that I got a girl on the first pick? 6 out of 15. So notice that probability changed, right? It's not the same as it was. Now, if I put that girl back in here and reshuffled the deck and said, okay, let's draw again, then it would still be 7 out of 16. What I'm saying is that when you sample without replacement, that leads to dependent events. Fortunately, if your sample size is kind of small compared to your population, the difference in these two things is slight enough that we can kind of ignore it. We pretend that they are independent even if they're not. And it's called your 5% rule. So if your sample size is less than 5% of the population, then you can treat sampling without replacement as leading to independent events, even though technically it's not. You can treat sampling without replacement as leading to independent events. So it's your 5% rule. And it's something that the author does use. So I would hope that you can get comfortable with it. No, it's leading to problems 10 and 12. Yeah, appreciate it. It does kind of apply to problem number 8 because presumably when you're sampling these 500 people, you're not sampling with replacement. You don't poll somebody and then put them back in the pool to be polled again. All right, you've talked to them once, you got their information, that's it. But here, what's happening is that 500 people is taken from a pool of all smartphone users. And that's presumably a really big pool. In fact, I think, Charbel, you were showing me some data on the iPhone. And there's over 1 billion of them that have been made and are in use, I think, right? So up to and including the 8. So, 500 is a pretty small number. It's certainly less than 5%. So you don't have to worry about the independence here. Let's take a look at problem number 10. Ten different senators from the 113th Congress are randomly selected without replacement. The number of terms they have served are recorded. Okay, so let's work on this one. do we have a fixed number of trials? Kayla, what do you think? Do we have a fixed number here? Okay. All right, so read it again. 10 different senators from the 113th Congress are randomly selected without replacement, and the number of terms they have served are recorded. So n equals 10 is our fixed number, so we're okay here. Second question is, are these independent? Well, remember they were sampling without replacement. So is that going to lead to independent events? Does the 5% rule apply? Well, you've got 10 senators out of 100. Sounds like 10% to me. So sampling without replacement, not independent events, nor can you apply the 5% rule. So this one's a failure. It does not satisfy the conditions of a binomial random variable. Let's go just a little bit further here. Are there two possible outcomes? How many terms can a senator serve? A lot, really, right? I mean, I think John McCain's on his 5th. I think Strom Thurmond, who was from like South Carolina or someplace in the Carolinas, probably served like a gazillion. He was in his 90s when he died, and he was a senator since he was like 30 or something. So quite a few terms from him. But there's more than two possible outcomes. So it fails this one, it fails this one. My son would say it's an epic failure, all right? It just fails. It's not even close to a binomial random variable. Let's look at problem number 12. So this is not a binomial random variable. Are you comfortable with our conclusion on 10? Please. Yeah, it was sampling without replacement, which leads to dependent events. We can kind of wink and nod at that as long as it passes the 5% rule. But it doesn't even pass the 5% rule. So it's just not independent events. Okay? All right. No, I do appreciate the question. Thank you. Investigating dates. All right. So in a survey sponsored by TGI Fridays, which is kind of an unlikely source to sponsor this, what are they prying into your business for? 1,000 different adult respondents were randomly selected without replacement. Each was asked if they investigate dates on social media before meeting them. Responses consist of yes or no. So when you get a date on Tinder, do you go look at their Facebook page first? I don't know. It's a question for you to answer, but let's look at the more relevant question, and that is this a binomial random variable? So Julian, is there a fixed number of trials here? How many? Yeah, 1,000. So 1,000. So yeah, we have a fixed number of trials. These are randomly selected without replacement. So first one is fixed. N equals 1,000. So we got that. Second one is, are these independent? What's your answer on that one? Lauren? Do you think these are going to be independent events? Why? All right, they're random. And what somebody does with respect to checking out dates on social media is probably independent of another ones. But this is also being sampled without replacement. Sampling without replacement leads to dependent events. But is there a workaround in this case? Yeah, 5% rule. Presumably, you're sampling from adults in the U.S., which is going to be a really, really big pool. I think the population of the U.S. is like 325 million or so. So it's certainly less than 5% of that sample. So we say yes by the 5% rule. Are there two possible outcomes? Yeah, yes or no. So we got that one. And is this probability the same throughout the trial? Yeah, it's going to be the same. So you're going to have a certain percentage of people that say that, and even though you're sampling without replacement, that percentage is not going to change much. So same probability, yes. So it is a binomial random variable. Yay. All right. Let's, are we okay with this one? Now, the importance of independence is coming back again, right? Understanding independent events and the 5% rule. I'll try and be careful on the exam to state explicitly what the population is, but in a lot of these problems, I think you pretty much assume that the population is adults or adults in the U.S., stuff like that, so that your sample size is never really going to exceed the 5% rule. 5% rule applied to the U.S. population would mean the population of your sample would be in the millions, and I just don't ever remember seeing a sample that big. Let's go back now and let me fill in for you how to actually calculate these probabilities. So it's going to be right here. Let's let n be the number of trials. X is the number of successes. P is the probability of success. So then your probability density function, or the probability of X successes out of n trials like this, works like this. P of X is going to be the number of ways you can have these n successes, or X successes out of n trials. So that's n choose X. This is what we did for problem number 1. We did 5 choose 2. Because it doesn't matter in what order these things come. A success is a success whether or not it's the first or the last one. Second part is a probability of those successes. So that's P. P to the X power. We had 2 successes in problem number 1, so it was 0.2 or 0.42 squared, and the rest of them were failures. So it's going to be times 1 minus P, which is your probability of failure, to the n minus X power. Now sometimes we use letter Q as the probability of failure. So n choose X, P to the X, and Q is equal to 1 minus P. Q to the n minus X. Now there's good news for you. There's abundant technology for us that allows us to calculate these probabilities without actually having to get our hands too dirty on that stuff. So let's practice with it a little bit. I'll show you how to do it on the graphing calculator and on Google Sheets. Let's start with the probability that we've already calculated, which was a probability for problem number 1. So, for example, In problem number 1, n was equal to 5. Probability of success was 0.42. And we want x equal 2 people to actually, be in favor of getting a package delivered by a drone. Okay. Let me show you how to do this on your graphing calculator, and then we'll do it on Google Sheets. On your graphing calculator, graphing calc, you're going to hit the second key, then the vars key, and I think it might work it out for you. The second key, then the vars key, get you up here to a place called distribution. So second vars, and then you want to select binomial PDF. If you're not sure how to run this command, you can press the plus key and it'll tell you. But I think if we press the equals key, it'll run you through it pretty good. How many trials did we have? Well, there was 5 people. What was the probability of success? 0.42. How many successes did we want? 2. And then just come down here to paste. And there we go. So that does all of it for you. Remember all that stuff that we did just a minute ago? Yeah. It's so cool. Technology is awesome. So, probability that x equals 2 here. Let's see. P of x equal 2 is 0.34417, etc. Now, let's do it off of Google Sheets. Yes? Let me see your calculator. Okay. If yours is not up to date with the operating system, that's okay. Let's go through this for those people whose operating system is not up to date. So you hit the second key. Yeah, sorry. You hit the second key and then the vars key. I always cursor up rather than cursor down. It's just a little faster to get here. Binomial PDF. And when you, let me just do it this way. What you're going to have to do when you get that command, binomial PDF, you're going to type in n, and then I think it's see if this will work first. Type in n and then p and then x. So in our case, it should be binom PDF of 5, comma 0.42, and then 2. And that worked? Okay. Catherine, tell me if that works. It works? Woohoo! Cool. All right. There's a very famous quote in Latin. So I guess I don't want to switch there. Switch over here. It's called. What's that? It's not working. Hang on a second. Let's see. Let's add another tab. Beanie Beachy. Beanie Beady Beachy. Purportedly, this was said by like Julius Caesar when he came to the site of a battle. And he said, Beanie Beady Beachy. I came, I saw, I conquered. So, kind of a cool thing. Beanie Beady Beachy. So, if you want to express a little triumph and rub somebody's nose in it a little bit, Beanie Beady Beachy. All right. Abby? The comma's above the 7. Above the number 7, you should see the comma. You're welcome. All right, let's try this on Google Sheets. And on Google Sheets, it's not that bad either. So, in fact, the nice thing is that Google Sheets kind of completes this for you. As with everything on Excel or Google, when you want it to do a calculation, you start out with an equals key. So equals, and let's start typing in binomial, B-I-N-O, and then it finishes off for you. Binomial distribution. So binomial distribution, and let's see what's you're going to type in. Let me do it over here first. So in Google Sheets, it's going to equal binomial distribution of x and then n and then p and then false. And we'll talk about that false, what that means in just a little bit. But x and then n and then p and then false. So let's do that over here. For our particular problem, that'd be binomial distribution of 2, 5, 0.42, false. And we should get the same probability that everyone else is getting. I'm hoping it's 0.42, false. Okay. John, did you get it? Yeah. Yeah. So binomial distribution 2, 5, 0.42, false. Did you switch those in the order there? Yeah. Okay. All right. Is everyone able to get that off of Google Sheets? So, on an exam, it's going to be up to you what you find most comfortable. Just pick one of them, or both of them. Whatever works for you. All right. False. That's a good question. Let me wait a little bit before I describe what false is. We're actually going to need to understand the difference. And really, well, let's describe it now. So if you have Google Sheets, then let's open up, let's clear out this sheet and type in the numbers 0 through 8. So let me see about cleaning this up. Where's the delete? More. No, I don't want more. Search menu. I don't want all these. Go away. Cut. There. Gone. So the other day, I think we worked with probability of the number of girls amongst 8 babies, right? So there's a total of 9 different possible events when you have 8 kids. Because you could have 0 girls, 1, 2, 3, all the way up to 8. So in addition to 1 through 8, you've got the number 0. That gives you 9 events that can happen. Does that constitute a binomial distribution? Number of girls amongst 8 births. Well, fixed number of trials? Yeah. Independent? Definitely. 2 outcomes? Yes. And same probability of success throughout the trials? Yes. So this is a binomial random variable. So let's do it this way. Type in equals binomial distribution. But rather than type in the numbers one at a time, like 0, 8, 0.5, etc., instead of typing in that first number, I'm going to type in this cell. So that way I can eventually copy this command all the way down. So click that first cell, comma, and then there was 8 trials here, so comma 8. Probability of success is 0.5, comma, and then false. So that gives us the probability that amongst 8 you have no girls. You'd have to be it's a pretty rare event not to get any. Now, let's copy that and paste it all the way down. So those are your probabilities. Notice that it's symmetric, right? Probability increases until you get to 4 and then decreases, but it's symmetric around that middle probability that x equals 4. What if I did the same thing, except this time I type in true? So equals binomial distribution. Again, click column A. So A1, comma 8, comma, 0.5, comma, true. And at least with the first one, it doesn't seem to make a difference. No. In fact, they're identical. But let's copy this and see if and what happens. And after the first one, there is a difference. So what's going on here is that to get the second column, you're adding things up in the first column. So at x equal 1, you're getting the probability that x is less than or equal to 1. So it's adding up these first two probabilities. And then here it's adding up these first three probabilities. So you're getting a cumulative version of these probabilities. So down here, this is the probability that you have up to and including 6 girls in these eight children. So it's just adding things up. Notice right down here, when you get down to the very end, it adds up to 1, which is reassuring. It should add up to 1 because it's a probability density function. And we learned that the other day, that this total has to total up to 1. So, Sanika, does that answer your question? All right. We're going to actually come back and use this idea in a little while. All right. But right now, I want to practice calculating with this probability density function just a little bit more here. So, let's try problem number trials. Let's try problem number 22. If 20 adult smartphone users are randomly selected, find the probability that exactly 15 of them use their smartphones in meetings and classes. Well, I know for a few of you that probability is 1. All right, but I'm not going to call you out here. Up above, they say that LG did a survey and that 54% of them use a smartphone in meetings or classes. So, okay, that's cool. Is this a binomial random variable? Fixed number of trials, 20. Independent, yeah, I think we can probably apply the 5% rule here without any problem. We get independent events. Let's see, 2 outcomes. Either they used it or they didn't. And the same probability of success is going to be about 0.54 throughout the trial. So, okay. So right there, this is going to be a binomial random variable. We want 15 out of 20 to say yes, and here's your probability of success. So either do it on your calculator or do it on Google Sheets, but try and calculate that probability of success. Should be a little bit over 3%. That one. So either do it on Google Sheets or on your graphing calculator. Okay. Are you getting about 0.30, what was it, 9? Yeah, should be about 0.309. Either way you do this. So let's just take a quick look at it with the graphing calculator. Binom PDF trials was 20, P was 0.54, X was 15. So there we go, 0.309. Nice. We can do that in Google Sheets. So let's take a look at that in Google Sheets. And I'll also do something else in Google Sheets here. Equals binom distribution. A little too fast. Binom distribution of 15, 20, 0.54, false. So we get that. What if I had done this calculation, except instead of false, I put true? What it's going to give me then is the probability that up to and including 15 people said that they used their smartphones. So it'd be 0, it'd be the probability of 0 plus the probability of 1, 2, 3, all the way up to 15. And that probability is going to be hugely different. So this is the probability that up to and including 15 people use their smartphone. So it's the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. False says whether or not you're accumulating these. So this is false here in this example, so you're just going to get the probability. If you set it to true, you get all the probabilities up to and including that added up. So if I added up all these probabilities, then I should get this one right here. If I add up all these probabilities, I should get this one right here. So that's what it's doing for you. Your graphing calculator has its own version of this. Instead of doing binomial PDF, you can do binomial CDF. And it'll do that same thing for you. It gives you that calculation. So it's up to you what you find most convenient, the graphing calculator or Google Sheets. And I think you can even do this in StatDisk as well. Let's move on to problem number 40 here. Talk a little bit more about CDF and PDF. And one last most important thing, and that is introduce the means here. So for a binomial random variable, with probability of success equal P, we get a couple of things here. I should probably put n trials. Let me define two things here for us, mu and sigma. What's mu stand for? The mean. So mu is the mean. Mean of the binomial random variable is simply going to be n times p. What's sigma stand for? Standard deviation is going to be the square root of n times p times q. And as a reminder, how do you calculate q? Thank you. It's 1 minus p. So if p is the probability of success, then the probability of failure is q. Failure. Or 1 minus p. So that's nice. What that's saying is that for a binomial random variable, instead of having to do all that lengthy stuff where we did the other day, where remember you did column of x times p of x, and then add it up, and that gave you your mean, and then you had to use the mean to calculate the variance, and then you had to square root of the variance to get the standard deviation. Wow. For the binomial random variable, all you need to know is n and p, and then you can get everything else. So that's kind of nice. That's going to help us out a lot. we're going to apply that to problem number 40. Has anyone ever heard of Gregory Mendel? Or Gregor Mendel, I think was his name. Father of genetics, did some experiments with plants, etc. He's the one that discovered that, there's traits that are hereditary and they're probably passed on by some mechanism, which we now know is genes, etc. Let's see, where do I have? I think it's right here. So he did some famous experiments. And actually, much later, people figured out the results were a little bit too good. That the data was probably faked, but probably not by Gregory Mendel himself. Probably faked by one of his assistants, but don't know for sure. But the data certainly look suspect because they're just too good. So let's see here what's going on with problem number 40. One of Mendel's famous experiments with peas resulted in 580 offspring, and 152 of them were yellow peas. Mendel claimed that under the same conditions, 25% of peas would be yellow. Assume that Mendel's claim of 25% is true, and assume that the sample consists of 580 offspring. Use the range rule of thumb to identify the limits separating values that are significantly low and those that are significantly high. Based on the results, is 152 yellow peas either significantly low or significantly high? Well, let me help you out with that this way. So this is problem number 40. We had n equals 580 peas. Probability of success was 0.25. And the question was, well, what's typical? What would be significantly low or significantly high? And for that, we're going to use the range rule of thumb. Mu minus 2 sigma to mu plus 2 sigma. Those are going to be the range of your typical values. Outside of that, it's going to be atypical. So we're going to need to calculate these things. So mu equals n times p. 580 times 0.25. So that's 1/4 of 580. 4 goes in there 145 times. So that's what you expect on average, is 145 yellow plants, yellow peas. For the standard deviation, it's going to be the square root of n times p times q, or n times p times 1 minus p. In our case, the square root of 580 times 0.25 times 0.75. And I don't think I'll get away with doing this in my head on this one. Square root of 580 times 0.25 times 0.75 should be a little bit more than 10. So 10.428, etc. The clever thing to do for yourself is take this value on your calculator and store it. So on the lower left-hand side, right above the on button, is a store button. Let's store that value in X. X is next to your alpha key. Why? Well, because eventually I want to calculate mu minus 2 sigma and mu plus 2 sigma. So that's going to be 145 minus 2, and now I can just hit the X key. Minus 2x gives me 124.14. And that'll do that again for the plus case. 145 plus 2x. So 165.85. Yes. Okay. No, I appreciate that. So part A asks us to find the values that were significant and not significant. What's significantly high and what's significantly low. Our typical values, what we consider kind of normal or in the range of expectation, are going to be those values that are within 2 standard deviations of the mean. So either 2 standard deviations above or 2 standard deviations below. So the first thing we did was we calculated the mean and standard deviation. So here was the mean, and here was the standard deviation. So to find the range of what's kind of considered your typical values, we had to find this quantity, mu minus 2 sigma and mu plus 2 sigma. And so my shortcut, once I had this number on my calculator, let's pull that up again. I stored that in X just to make my calculation easier, just so that I didn't have to type in that number. I stored that in X, and then I calculated the mean, which is 145 minus 2X. So that gave me this part, my lower limit. And then the mean plus 2X. So it looked like this, 145 minus 2X and 145 plus 2X. So those are where my typical values lie. Anything outside that is atypical. Anything is either significantly low or significantly high, depending on which side of this fence you're on. You're welcome. Thanks for the question. Anything else about part A here? Okay. Let's take a look at part B. It says find the probability of getting exactly 152 P's. So this is part B. Probability that X equals 152. It's probably going to be pretty small. Not terribly small, because I don't think it's too far away from what you expect, but not going to be that big either. Well, fortunately, you've got a lot of calculator, or a lot of resources here that you can help calculate this probability. This is a binomial random variable. N equals 580, P equals 0.25, and X equals 152. Calculate this any way you want. Equals binomial distribution of 152, comma 580, comma 0.25, comma false. False because I don't want the probability of everything up to and including 152. I just want 152. Alternatively, on your graphing calculator, it's binomial PDF of 580, comma 0.25, comma 152. Let's see what you get on that. Do that here. Equals binomial distribution. Okay, so a little bit more than 3%. Are you able to get this number off your calculator or whatever device you're using to get this one? Yeah? Okay. All right, good. Thank you. Now the next one's a little bit trickier. And this is where I warned Sanika, or I mentioned to Sanika, that we're going to go back and look at that CDF command. Because up here, if I wanted to find the probability that X was less than or equal to 6, it's pretty easy, right? I just can add all these up, or it's my CDF command right here, that's fine. I could also use that once I find the probability that X is less than or equal to 6, by the complementation rule, I can get the probability that x equals 7 or 8. In part C, though, this one's kind of tough. They want the probability that there's at most 152 yellow plants, or yellow peas. Probability that x is less than or equal to 152. Was it more? Is it less, or which one? Is it more? Yeah, more than 152. My bad. So this runs the other way. X is greater than or equal to that. So, wow. This could be a real problem even with Google Sheets, unless you're going to be really clever. Because really what you would have to do, if you're doing this with your PDF, is you'd have to have this run out all the way down to 580. And then you'd have to add up all the probabilities starting with 152, 153. Ugh, that'd be a pain. So we're going to use the CDF instead. Yes? Yes. That's pretty much what we're going to do. We got to be a little bit careful about that, but let me help everyone catch up to you. So let's look at the events surrounding this. So let's just type in a few events. So I got 152, 153, 154, 151, 150, etc. So there's a lot more. They go all the way out to 580 on one end and 0 on the other end. But the probability I'm being asked to calculate is the probability that x is greater than or equal to 152. So that's going to start at 152 and move out this way. So everything to the right. Well, there'd be a lot of calculation. Remember, we can calculate things using the complementation rule. So that would be probability of 1 minus this. So I've got to describe this event. How would I describe this event here in salmon or pink? What's that probability? And be careful. Careful of where it starts. Andrew? What would this probability be? How would I describe it? What less than what or greater than what? All right, let's go less than or equal to 151. So here's where you would use your CDF. Because if I use my, here's where I use the true here. If I use true here, I'll get the probability that x is less than or equal to 151. So I can get that probability, and by the complementation rule, I can get this probability. If you're stuck using a graphing calculator, you can use, instead of binomial PDF, you can use binomial CDF. So let's see what this looks like on Google Sheets, and then I'll do it on the graphing calculator. I think we'll be done with this section. So on Google Sheets, it's going to equal binomial distribution of, where is it, 151, and then 580, and then 0.25, and this time true. Actually, I want 1 minus that probability, right? So let me do that over here. Equals 1 minus this one right there. Yay. So that's my probability, 0.2650. So 1 minus 0.7350. If you're doing it on a graphing calculator, you can do something similar. They have a binomial CDF there. This one here. So if you go to distributions, binom CDF, let's see, we'd want 580 trials, probability is 0.25, 151. Thank you. Do we want 151? No, yeah, 151. And if I take 1 minus that answer, then I get the same probability, 0.2650. Now, some of that is a little bit nuanced. If you catch on to it, great. If you don't, what I'm going to do, my kind of workaround for you having to know all this stuff about CDF and true and false and stuff like that, is the tables I give you are going to be small enough that you can do it differently. You can just sum it up. If I need the probability, for instance, that x is less than or equal to 6 here, then I can just do, all right, sum of these numbers. So I'm not going to make you worry about that CDF and stuff like that. But we did get a question about that, true or false. So you at least know a little bit more about Google Sheets now and how some of these things work in Excel. Whew. Let's put an end to this one. Questions on problem 40? Yes?
So in an exam, like, how would you ask us to
So, well, I would suggest that you just by default use false. And then depending on the event, if I ask you for the probability that, say, x is greater than or equal to 5, then you could just say, look at this and say, oh, okay, well, I need these, and sum it up. So we do sum of these 4. All right, I'm not sure what I'm wrong. Let's try it again. Sum of these 4, and you just calculate it directly. Just add up what you need. All right. I think that this CDF stuff is probably a little bit intimidating for people that aren't used to it, but you've seen it. So if you're comfortable with it, great. If not, I'll give you distributions that are small enough that you can just add up what you need. For homework, try 1 through 39 in both editions. Now, in the 12th edition, that's going to be section 5.3. In the 13th edition, it's going to be section 5.2. So it depends on what edition that you're working with as to what you're going to end up doing. So homework is 1 through 39, 5.3 in the 12th edition, and 5.2 in the 13th.